Hey, how's it going? Welcome to Physics with Mr. Shives, and that's me, Mr. Shives. Hope you're having a wonderful day today. Thank you for coming to YouTube and checking out this video and wanting to learn something. That's the first step. The first step is always the toughest. You've got to have some want to and have someone willing to teach you, and I'm here willing to teach you as long as you're willing to learn. So let's go ahead and get started. Today we're talking about ramps and inclines, and let's see how this applies with our physics, see what's up. Alright, real quick, first thing we're going to do is we're going to make a little note. We're going to do a definition for work. Quick formula for work. So work, W-O-R, this W means work. Work is equal to your distance times your force, F-O-R-C-E. Distance times force. Work is directly proportional to the distance. That means if your distance goes up, if your distance increases, then your work will also go up. If your distance goes down, then your work will also go down. So directly proportional means that they are tied directly to each other. When one goes up, the other goes up. One goes down, the other goes down. Let's go to work. This is the second one. Work is directly proportional to the force applied. That means that means when your force goes up, your work goes up. What happens if your force goes down? That's exactly right. Your work will also go down. So yeah, they are also directly proportional. Go ahead and write that down if you haven't already. Alright, here's a huge note. If you apply a huge force, a gigantic force, but the object doesn't move, is there work being done? The example is, let's say I stay in this classroom and I gotta push this wall over. My job is to push this wall for 24 hours. I'm pushing. 24 hours have passed. You come into the class, you see me super tired. I'm all sweaty. I'm really tired. Oh my gosh. And you ask me, hey, how much work have you done? I say, well, look at me, I'm all tired. And then you look at the wall. Has the wall moved? If it has not moved, there is no work being done. So when your distance is 0, your work will be 0. Here's why. Your work is equal to your distance times your force applied. Work is equal to 0 times force. I don't care how big this force is. That 0 is going to turn him to 0. Your work will be 0. So if it does not move, there is no work. Alright. Next one. Here's some examples. First thing I want you to do is, I want you to write this down, please. Example number 1. We're going to draw a surface, some lines. We're going to draw a ramp on that surface, and we're going to draw a box on that ramp, or a block, whatever you want to call it. We're going to sketch a free body diagram of this drawing right here. So first you draw your dot for your block. Then you're going to draw, the first line we draw is our mg, it's our mass times gravity. And then we have a surface here, don't we? Isn't the block on a surface? So we have a surface, so there is a normal force that's going perpendicular to the surface. And let's say this block is only being held by friction. Friction is the only thing keeping this block from moving. Well, what direction would the block want to move if there was no friction? Well, the block would want to just slide down this ramp. Do we agree? Of course we agree. And what do we know about friction? Well, we know that friction opposes motion, so since the box wants to go down and to the left, down the ramp, friction must be pulling it up the ramp. That's your friction force. Is that right? There's your free body diagram, and you're done. No big deal. Let's talk about example number 2. Let's say, same thing. There's your surface, there's your ramp, there's the box. There's point A, and let's say this point is point B. And this angle, let's say this, I don't know, let's just call it theta. We don't know what it is. We are going to apply a force to that box. Alright? If we change, I'm sorry, let me just read this to you. We're going to move this box from point A to point B by applying a force to it. I don't know how big the force is. I don't know how far A and B are, but this incline is some kind of angle theta. We don't know what the angle is, but they call it theta. If it was to change, if we increase theta, that means we increase the angle. We leave everything else the same. A is the same. B is the same. The box is the same. You have your force. When we compare this with our work formula, Let's put it right here. Our work is equal to distance times force. This one, work is equal to distance times force. Did the distances change from each of these guys? Did the distance change? Did A get further? No, the distances stayed the same. Did your force change? I don't know, let's see. Here's this block. The incline's not so steep, so we gotta apply some force to get to it. Here's this block. The incline is more steep, so do you think we'll need more force or less force to push this block up that ramp? Good, we're gonna need more force to get that block up the ramp. So our force is going to increase. Our distance stayed the same. If your force increases, what happens to your work? Yes, it increases as well because they are directly proportional. So there we go. Force increased, your work increased. You're good. Next one. This is the biggie right here. Let me start a new slide for it. Here's the big example right here. Example number 3. Let's say, here's the surface. 2, 3, 4, 5, 6, 7. Be sure you draw the right amount of lines underneath that surface. Totally kidding, there's no need. You just shade it in as you want to. Let's say the angle is at 30 degrees. I just made that up. Let's say this block weighs 4 kilograms. Let's say this block is being held by friction. Not moving. Friction is holding it. Alright? I want you to find what the friction force is of this block that's holding it. Well, let's see. First step we will do is we will draw your free body diagram. There's your box. First line you draw is your mg. Well done. What else do we have here? We have a surface here, and we know that normal force is perpendicular to that surface. So you have a normal force. And you have friction force. What direction is friction force going? Is friction force going down the ramp, up the ramp? What do you think? Well, this block wants to slide down the ramp, but thank God for friction, so since the block wants to move, friction force will oppose it, so friction force must be going up the ramp in that direction. Friction force. There you go. That looks good to me. Alright, next thing we're going to do is we are going to create an X and Y axis. Don't draw this. Don't draw this. I'm just going to sketch it over here. Let's say I did this. Normal force, friction force, mass times gravity. If I was to draw the X and Y axis on that free body diagram, change the pen color, let this be the Y axis, sorry it's not straight, then let this be the X axis. Well, how many of these lines are in line with one of the axes? Well, let's see, there's nobody on line with the X, but there's one on line with the Y axis. So how many guys are not in line? 1, 2. There are 2 guys that are not in line. So we probably don't want to do that because there'll be more work to do. So we are not going to use your up and down to be Y and your side to side to be X. We're not going to do that there. Instead, we're going to go over here and let your FN be your Y axis. Let that be the Y axis. So if this is my y-axis, then who's my x-axis? Where's my x-axis at? It's going to come from this direction right here, this friction force in this case. So when we draw this, who's the only person that's... Okay, how many lines are actually in line with one of the axes? Good, your Fn is in line, and now your friction force is also in line. So we only have one guy that's not in line. Do we agree with that? Good, I agree as well. So this is going to take less work to do, and I know we're all about working smarter, not harder, so we're going to use this. So we're going to redraw this free body diagram. Let me put a little note here. We're going to redraw, but as we redraw, we're going to rotate it. That way we have our x and y axis looking regular. We don't want to be like this the whole time, looking at our x and y axis. So who was our... Here's your dot. That is your Fn. And that's your y-axis. Your friction force is your x-axis. And your mg is in this direction. Your mg is in that direction. Correct? Good. Now the only guy we need to fix is who? The mg. Perfect. So here's how you're going to fix your mg. Here's where it gets a little weird. Mg. That's your mass times your gravity. Do you remember when we did vectors and we did displacement and all that, and you had to break up those vectors into x and y components? Well, we're gonna do the exact same thing with this mg. We got to break him up into his x component and then into his y component. So here's how we're gonna do it. To break him up into his x component, you're gonna do this. To break him up into his x component, you're going to do this. You're going to take your mg, whatever it is, and then what's the trig function that we use when we did projectile motion and vectors? What do we use for x? What will always give you the x? Cosine, right? But we can't use cosine here. It would be cosine, but we cannot use it. We are going to use sine. Hang on real quick. We're going to use sine for this. So sine of who? Sine of theta. Whatever the angle is, whatever they give us, for example, they gave us 30 here, we're going to put the 30 right there. To find the y component, we're going to go mg. That's right, we're going to need to use cosine for this. These trig functions are going to switch. They switch for this because we're doing ramps and inclines. When you are doing ramps and inclines, you will need to switch trig functions. So now your x component is with sine, your y component is with cosine. When does that happen? When you are doing ramps and inclines. Got that? Alright. Now let's actually plug in some. Oh, I forgot to tell you this super important thing. I'm sorry, I should have told you this first. You'll see this in your textbooks, you'll see this online, you'll probably see it from other YouTube people trying to teach you physics. Your x component will be labeled as your m. Sorry, get my marker weird. It'll be mg parallel. That means parallel to the surface. Notice, here's your friction force. This is the surface, right? What direction is parallel to the surface? Would it be up and down or side to side? It would be side to side as well. That's going to be your mg parallel component, which is your x component. The other part, your y component, is your mg perpendicular. So your mg perpendicular is your y component of the mg. So we're taking mg, we are breaking it up into two pieces, your y component and your x component. So your y component is your mg perpendicular. So I'm going to write it down on the y-axis. That's my mg perpendicular. We got that? Now let's actually find the mg parallel and the mg perpendicular. Let me change the color of this marker. I don't know, let's use, what about, I use that. Let's use this weird gold or orange, whatever it is. So here's my work for mg parallel. Mg, I'll write it over here, I guess. Mg parallel is going to be equal to, let's see, what's the mass of the object? M is mass. Let me just write everything down. Mg sine theta. M represents the mass. Well, we know this is mass because it says kilograms, so it's 4 kilograms, so it's going to be 4. What is G? G is the force of gravity, so you have 9.8. Could be, leave it as negative 9.8 if you'd like. Sine. Punch that in the calculator. Well, first let's do this. 4 times negative 9.8 gives you a 4 times negative 9.8 gives you a negative 39.2. Now we have sine of theta. Let's see, theta is the angle measure. How big is that angle right there? 30 degrees. So I'm going to put sine of 30. So we type this in our calculator, negative 39.2 sine 30. Press enter, you get a negative 19.6. Erase the negative because this vector is going in the left direction, which means it's already going to be negative, it'll be taken away. So your mg parallel is going to be 19.6 newtons. It's right there. Mg parallel is equal to that. And I put it right here. I put it positive here because it's already going in the negative direction. I don't want to put the negative there. Now let's find the mg perpendicular. Let's take the ink color, change it to purple. Here you go. Mg perpendicular is equal to your mass times gravity. What do we say? Cosine of theta. So I got mg, sorry it's getting a little sloppy. Mg perpendicular is equal to, what's the mass of the object? 4 because it says kilograms. So we got 4. Gravity is 9.8. Let's just leave the negative out, that we don't have to take it out later. 9.8 cosine of 30. So 4 times 9.8 is 4 times 9. I know we just did it, but I'm pretending like I'm a student. It's 39.2. So we have 39.2 cosine of 30. Type that in, 39.2 cosine 30. That gives you a 33.94 newtons. Oh, sorry, 32.95 newtons. And that is your mg perpendicular. Mg perpendicular. That's what we got. So let's put this in for mg perpendicular. 33.95. Alright? So we have that. So what's your normal force going to be? Well, your normal force is always going to be this piece, this mg perpendicular. It'll always be the same as your mg perpendicular. So I'm going to write 33.95 newtons up there. And if this box is not moving, let me change this color. Sorry. Alright. If the box wants to slide down the ramp at 19.6 newtons, if that's the force it wants to go down the ramp at, then what must the friction force be that's holding it up there? If the box isn't moving, if it's constant, if it's staying in the state that it's in, what must this friction force be? It's got to be equal to the weight of it that wants to go down the ramp, so it must be the same. So your friction force is 19.6 newtons. It's got to be that. Alright. This goes, if you see the words constant speed. By the way, we're done with this problem. You did a wonderful job on this problem. Terrific. If you got it, great. If not, we run the video, see where you got lost. And hopefully I covered everything on this. If not, please send me a message or hit me, do a comment or whatever you need to do. And I will definitely get back with you. If you see this constant speed in a word problem, that means that your net force is going to be 0. All the forces will cancel out. Constant means it won't change. I'm going to write that little bullet there. It won't change. Your acceleration is 0. Your friction force is the same as your force applied. All that. All your forces will cancel out when it's in constant speed. Does that mean that the object has to be staying still? No, it doesn't. If this bamboo is staying still right here, I'm pushing it up with, I don't know, a Newton, and I'm pushing it down with a Newton, it's staying still. What if I'm sliding this bamboo over to the, what side would this be for you? To the left side. Here we go, it's going to the left side. I'm still pushing with those forces. Those forces canceled each other out. It was still at a constant speed because the speed was not increasing or decreasing. It was staying the nice steady speed right here. So it'll stay in whatever speed it's going at, and it'll stay at rest. When you see constant speed, please use that. Please be aware of everything we just talked about, and have a wonderful day, and I'll see y'all next time. Thank you.